everyone, welcome to Learning at 11th Hour. Today I'm going to show you how we can design a clocked sequential circuit from a given state diagram. So there are about 4 steps that are majorly involved in this, apart from the final logical diagram. So the first step is called as the state reduction. The second step is to obtain the state table. The third step is to perform state assignment, and this is followed by obtaining the flip-flop excitation table, and from that we obtain the expressions for the flip-flop inputs and the outputs, and lastly we have the implementation. So the 4 major steps, like I said, are state reduction, the state table, state assignment, and flip-flop excitation table. From the flip-flop excitation table, we can obtain the equation for the flip-flop inputs and outputs using the K-map, followed by the implementation of these expressions. So here I've been given this problem where I need to implement this particular uh, circuit using the JK flip-flop. So all the information that I have is the state diagram. So from this, we need to obtain the state table. So the first step is going to be state reduction as per this sequence. So what is the meaning of state reduction? So when there are multiple states, right, when there is a larger state diagram with multiple transitions, there might be a possibility where some of the transitions may be redundant. In such cases, we go for something called as state reduction. This would be discussed in another video. This particular example has this diagram already in its reduced form. So we directly move to the state table. So we know that the state table is going to have the present state, the next state, and the output. So as far as this state diagram is concerned, there seems to be no output as such for this particular circuit. So what I'll do is I'll conveniently get rid of the last column. Now we see that uh, the transitions are dependent upon one particular input. So there is one external variable, and let me call that as x. So x is my external input. So the next state would depend on two things: x is equal to 0 and for x is equal to 1. The present state is represented using 2 bits. So let me call them as A and B. Now, looking at this, we can actually determine how many flip-flops we need. So every state is actually represented by 2 bits because there are a total of 4 states. So we require a minimum of 2 bits to do that, which means we will require 2 flip-flops to implement this particular example. So I can say that M is going to be the number of flip-flops if 2 to the power m is the number of states. So in this case, 2 to the power m, in this case m is going to be 2 because we have 4 states over here. Therefore, m becomes 2. Therefore, we have 2 flip-flops, flip-flop A and flip-flop B. So A, B put together represents one particular state. So let's update this table. So we can have 4 possibilities: uh, 0, 0, 0, 1, 1, 0, and 1, 1. So our present state could be one of these 4 uh, possibilities. So now we have our state diagram over here. When the present state is 0, 0, and the input x is 0, the transition happens to the same state itself. So the next state becomes 0, 0, 2. But from 0, 0, if I get an input x equal to 1, then it makes a transition to the next state 0, 1. as per this arrow. Now let's focus on the state 0, 1. So when the present state is 0, 1 and the incoming input is 0, it makes a transition to the next state 1, 0. And if the incoming input is 1 itself, then it is going to remain in the same state. Again, let's focus on the state 1, 0. When the present state is 1, 0, there are two possibilities. For x is equal to 0, that's one possibility. It's going to remain in the same state. For x is equal to 1, it is going to move to the next state. And here it shows it goes to 1, 1. Now looking at the state 1, 1, for input 0, it is going to remain in the same state. And for input 1, it is going to go back to 0, 0. So this actually forms my state table. Now the question says that we need to uh, use the JK flip-flop for the implementation. So how can we do that? So keeping in mind that we need to use the JK flip-flop, we need to frame the excitation table from this given state table. So let's try and do that. So here what we have is, we have the present state with A and B. So I'll call it as A and Bn to represent the present instant. We have the input, which is X. We have the next state, which is An plus 1, Bn plus 1. And then we have our flip-flops inputs. So in this case, we have two flip-flops. So we are going to have JAKA and JBKB, because we are going to use the JK flip-flop for this particular implementation. So these are the headers for my excitation table uh, for the JK flip-flops that we are going to use. So now we can fill up this particular table, keeping in mind that we have the state table over here. There are three inputs, an, bn, and x. So when there are three inputs, we can fill it up as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now, from the state table, we can actually fill up the next state, which is pretty simple. So for x is equal to 0, when the input is 0, 0, we have 0, 0. And for x is equal to 1, we have 0, 1. For 0, 1, for x is equal to 0, we have 1, 0. For x is equal to 1, we have 0, 1. For 1, 0, for x is equal to 0, we have the next state as 1, 0. For again 1, 0, for x is equal to 1, we have 1, 1. The last one, for x is equal to 0, 1, 1. For x is equal to 1, it is 0, 0. So now we have the present state, that is an, and the next state an plus 1. So let's just focus on these two columns right now, so that we are able to obtain the excitation for the JK flip-flop A. So that is JA and KA. So in order to do that, we need to remember that the excitation table for JK flip-flop is as follows. So we have, say, Qn plus 1, J and K. This is the excitation table of my JK flip-flop. So we would have this as 0 don't care, 1 don't care 1, and don't care 0. So with the help of this table, we can fill this particular column for JAKA, observing only the present state AN and the next state AN plus 1. So this is pertaining to flip-flop, JK flip-flop A. So the present state is 0, 0, then JK will be 0 don't care. For 0, 0 again, we have 0 don't care. For 0, 1, we have 1 don't care. For 0, 0 again, we have 0 don't care. For 1, 1, it is going to be don't care 0. For 1 1 again, don't care 0. 1 1 is again don't care 0. 1 0 is don't care and 1. In a similar way, we can actually fill up the excitation inputs for JK flip flop B by just observing Bn, the present state Bn, and the next state Bn plus 1. So we have 0 0 is going to be 0 don't care, 0 1 is 1 don't care, 1 0 is going to be don't care 1, and 1 1 is going to be don't care 0. Then we have 0 0 again, 0 don't care, 0 1 again, 1 don't care, 1 1 is don't care 0, and 1 0 is don't care 1. So in this manner, we have actually filled up the entire excitation table for my JK flip-flop A and JK flip-flop B. We now need to obtain the expression for JA, KA, and then for JB and KB. So in order to do that, we need to frame the K map where for the flip-flop A, the inputs are going to be A and B and X. And for flip-flop B again, the inputs are going to be A and B and X. So this is going to be a 3-variable K map in each of these cases. So we have JA. I'll keep X here and A and B over here. So now we can frame this as for JA we have 0 1 0 as 1, and everything from 4, 5, 6, and 7 as don't cares. So 2 is going to be 1, minterm 2, 0, 1, 2. 2 is 1. 4, 5, 6, and 7 are don't cares. So therefore, we can group these two together to form a pair, and therefore the expression for JA would be, analyzing the rows, nothing is common. Analyzing the columns, we have AN, BN dash. So this is the expression for JA. Next, we have to obtain the expression for KA. In order to do that, we observe the column for KA. We see that it is don't care for 0, 1, 2, and 3. So 0, 1, 2, and 3 are don't cares, and 7 is going to be 1. So 4, 5, 6, and 7. So now we can form this to be one of our groups. So it's a pair, and the expression for this particular pair is going to be 0, 1, 1, 1, 1, 0. So we can see that this is AN, BN. Similarly, we can obtain the K map for JB. So here we'll have 0, 0, 0, 1, 1, 1, 1, 0. And JB, analyzing the column for JB, we see that it is 1 for the minterm 1, 2 and 3 are don't cares. Okay. So 1, 2, 3 are don't cares. And 5 is 1, 6 and 7 are don't cares. 5 is 1, 6 and 7 are don't cares. So now we can frame a quad over here to obtain a smaller expression for JB. So JB here is going to be, analyzing the rows, none of them is going to sustain, but looking at the columns, we see that it's going to be BN. Now let's look at KB. So for KB, we have 0, 1 as don't cares. So 0, 1 is don't care. 2 is 1. Then 4 and 5 are don't cares. And 7 is 1. So we can now group the minterms in this manner and form a quad, and therefore the expression for KB now becomes BN bar. So having known the expression for JA, KA, JB, and KB, We can now implement it using the flip flops. So this is going to be flip flop A with J A K A as my inputs, A bar as the output with the clock, and this is going to be the second JK flip flop, JBKB, with B bar as the outputs and the clock. This being synchronous in nature, both the flip flops would be excited with the same clock pulse. Here, JB is BN, so we can just join the output B into JB, and KB is BN bar. So this is how we get it. Moving on to JA, the expression for JA is AN BN bar. So we will require an AND gate over here. So if this is BN, I can actually put a NOT gate to avoid too many lines. And this is AN. So both of them ANDed together should be JA. Then we have the expression for KA is ANBN. So both of them are here and we get it this way. So let me call this AN and BN, or rather A and B to keep it simple. So to avoid too many lines, I've just written the AN and BN directly. So in this way, we have obtained the logical implementation of the state diagram. So it is quite interesting to notice that there is no role as such played by X. So therefore, we can comfortably say that with every clock pulse, there is going to be a change in state. So rather, we can say the clock in this case is actually my X. So whenever we press the clock pulse, there is going to be a change of state happening with the help of this circuit diagram. So that's all with today's video. I hope the process of design of synchronous sequential circuits is clear to you all. If you have any queries, please don't hesitate to post them in the comments below. Thanks for watching.